Hello everybody and welcome to another video on my channel. Today we will be talking about the product rule and the quotient rule, two pretty fundamental rules in calculus, and of course proving them using the limit definition. Here are a few prerequisites, or stuff that you must know pretty much before going into the product and quotient rule. The first is basic derivative rules, like the power rule, the constant rule, differentiation of a trigonometric function. Number two is the definition of a derivative, the limit definition of the derivative, to be slightly more exact. Number three is concept of differentiable functions, which pretty much is kind of like continuous functions, except a little different, but it's not really needed to understand right now. Maybe in another video in the future I might explain a little more about differentiable functions, but for now, think of something that are close but not the same thing to continuous functions. And the fourth thing is notation. F dash of x, dy by dx, and d by dx. Now, why do we need the product and the quotient rule? The derivative of the rule says the derivative of a sum is the sum of the derivatives. So if I have f plus g dash is equal to f dash plus g dash, and I know it might be a little confusing to see that there's no x or anything, but this is just another way of stating functions. So if I have a function y is equal to x cubed, then y dash would be 3x squared, even though it could be said as dy by dx or y dash of x. Sometimes it's simpler and more efficient to put it as just dash without the x term. But the derivative of a product is not the product of its derivatives. Examples, d by dx of x times x squared. In reality, that would be d by dx of x cubed, and d by dx of x cubed is 3x squared. But if we multiply, so d by dx of x times d by dx of x squared, d by dx of x by the power rule is 1, and d by dx of x squared by the power rule is 2x, and that's not what the derivative of x cubed is, or just x times x squared in general. What we need special rules for products and quotients. And that's where the first of the rule comes in, the product rule. If we have a product of two functions, if f of x and g of x are differentiable functions, which is pretty much another point that you need to know, is all the examples that we're going to solve and all the differentiation problems that we're going to do anyways are pretty much always differentiable functions unless I say otherwise. And the only time I'll be saying that is when I've finished talking a little more in depth about differentiable functions. Then I might have problems for you guys to identify whether a function is differentiable or not. Now, what the formula states is d by dx of f of x times g of x is equal to f dash of x times g of x plus f of x times g dash of x. So, it's equal to the derivative of f of x times g of x plus f of x times the derivative of g of x. And here are a few other ways to write the product rule notation. So, first is fg dash, basically grouping fg, saying that they're multiplied by each other and just removing the removing the x for simplicity. The next is d by dx of uv, where u and v are functions of x is equal to u dash v plus uv dash. But the third and final method is to assume that we have a function y, which is equal to f of x times g of x, where f of x and g of x are two independent functions of x. Then y dash is equal to f dash of x times g of x plus f of x times g dash of x. Now here is a proof outline using the definition of the derivative. Now it doesn't have all the algebraic manipulation, as number one, that would take a lot of space up on the screen. And number two, this is actually slightly simpler than the quotient rule, which I'm going to show more steps for, since it is slightly more complicated and there are a lot of places to make very simple mistakes, but here it's slightly less common, so it could be an exercise you do after me showing you how the quotient rule works. So let's start with f of x is equal to u of x times v of x. Then apply the limit definition, so f of x times f dash of x is equal to limit as h approaches 0 of f of x plus h minus f of x over h. This is the limit definition, which we've covered lots. Then the third step, I wrote here substitute and manipulate algebraically. What happens is when we substitute, it's going to be u of x, v of x plus h, etc. Where when we have f of x equal to this, so f of h plus h is equal to u of x plus h times v of x plus h, and then minus u of x times v of x over h. Then add and subtract a certain term in the numerators. I thought this would be slightly more complicated to realize. Then do some more algebraic manipulation and apply a few limit properties, which were covered in my Intro to Calculus series. Please make sure to watch that. And the result is we'll get the product rule. Now this is pretty much only a proof outline, and much of the algebraic manipulation will have to be done by you. If you go in the comments and you decide to ask me, I'll of course explain the entire steps. Maybe I'll even create like a file or something, where like a Notion doc or something where I explain everything in math, just to show you the full thing. But otherwise, it would be a very good exercise for you to try it on your own. Let's move on to the examples for the product rule. So the first example is to find the derivative of f of x is equal to x squared times sine of x. So what we need to do is first, let's state the product rule. Now the form I'm going to state it as is, I'm going to say x squared is y of x and sine of x is z of x, but I'm just going to remove the x. So what's going to happen is f dash of x is going to be equal to y dash times z plus y times z dash. Now, this is pretty much the formula, but we also need to substitute our functions in. So f dash of x is equal to y dash. Now, if y is x squared, according to the power rule, that will be 2x times z, which is sine x. So 2x sine x plus y is x squared, then multiplied by the derivative of sine of x according to the trigonometric function derivative rules, which I covered last video. Make sure to go check it out. 2x sine x is equal plus x squared. Then it's going to be equal to cosine of x. And that's pretty much about it. That's our answer. It was pretty simple. Just plugging and checking the formula. No complicated terms at all. So there you go. There is the full solution of the problem. F dash of x is equal to 2x times sine of x plus x squared times cosine of x. Now, as you see, the solution over here is 2x times sine of x plus x squared times cosine of x. Now, what they decided to do is use u and v in the product rule formula. What I decided to do was use u and v. I work as a solo content creator, and so I don't really have any partners in this, although sometimes I might ask for a little help of some people I know to explain the concept. I especially did that for the non-Euclidean geometry, as I was quite confused, and by people I mostly mean online and a few of my friends. The next example is to find the derivative of g of x is equal to 3x plus 1 times x squared minus 4. Now, what we have to do is, of course, I'm going to skip stating the product rule, but we also need to identify the functions. So, g dash of x, if we say 3x plus 1 is equal to u and x squared minus 4 is equal to v, then what happens is we have 3x plus 1, so we have to take the derivative of that. That ends up being 3 times x squared minus 4 as z, then plus 3x plus 1 multiplied by x squared minus 4 derivative, and since negative 4 is a constant, the derivative is 0 for that, and the derivative of x squared is 2x. That's pretty much what it is. Then all we have to do is expand and simplify. So if we simplify the first term, 3x squared minus 12 plus then 6 squared plus 2x, then this is going to be equal to 9x squared plus 2x minus 12. So as you see, that example was slightly more complicated than the previous one, and it also involved a little bit of simplification. Let's move on to the solution, and it says over here, the steps are pretty much all the same. Substitute and simplify being the main part of the algebraic manipulation, identifying the functions, finding the derivatives, and applying the product. This is the quotient rule. The quotient rule is if we have a quotient of two functions, where of course f of x and g of x are differentiable functions, and g of x is not equal to 0, then d by dx of f of x over g of x is equal to f dash x times g of x minus f of x times g dash of x, all divided by g of x squared. Now you can already see how this is more complicated than the product rule, and proving this will also be slightly more complicated. But before we prove it, or rather give you the outline of the proof with some algebraic manipulation, let's discover some alternative notation. So all of these are pretty much the same thing. The last one being y is equal to, we're basically substituting for y, then we have y dash. The otherwise we have u by v. The other one is just where we have prime notation versus Leibniz notation, which is the d over dx. Quotient rule, this is the proof outline, or really pretty much the entire proof of the quotient rule. So start with f of x is equal to u of x divided by v of x. You already saw the limit definition, so we'll go straight to step 3 to substitute it in. So we have u of x divided by u of x plus h divided by v of x plus h minus u of x over v of x, all divided by h. Then, if we find the common denominator, what happens is u of x plus h v of x minus u of x v of x plus h divided by v of x plus h times v of x times h. So then we add and subtract u of x times v of x. Then what happens is we'll be able to factor everything out. Then we have to separate each of these and apply a few limit properties, such as the multiplication, limit, subtraction, addition properties, essentially to split it up into more manageable forms, to get u dash x times v of x minus u of x times v dash x divided by v of x squared. That was quite a complicated proof, but sometimes the examples can be much simpler, like this one. So let's find the derivative of f of x is equal to x squared plus 1 divided by x minus 3. What we need to do is first figure out what the functions are and state the quotient rule. So f dash x equal to, if we say x squared plus 1 is y and x minus 3 is z, that means we have y dash times z minus z times y dash. No, sorry, that's just the same thing. Y times z dash, sorry. Then that is all divided by squared. So that's the quotient rule. But then when we substitute, things start to get just a teeny bit more complicated. So y dash, where y is x squared plus 1, is 2x. 2x multiplied by z, which is x minus 3. Then we have minus y, which is plus 1. Then that is multiplied by the derivative of x minus 3, which is 1. Now after that, what we do is we divide this entire expression by z squared, so x minus 3 whole squared. Now these are just the first few steps in solving this problem. After that, we're going to have to do a good amount of algebra. What we have is 2x times x minus 3, that becomes 2x squared minus 6. 2x squared minus 6. Then if we have x squared plus 1 times 1, 1 is just x squared plus 1 times 1 is just x squared plus 1. So we flip the signs of everything. Then when we have x minus 3 squared, over here it should be x minus 3 squared, not x minus 3. Let me quickly redo that. We are back quickly right after fixing that. X minus 3 was supposed to be x minus 3 squared, so I quickly just adjusted that. Now we can go on to solving the rest of our equation. So this becomes 2x times x minus 3 is 2x squared minus 6. 2x squared minus 6. Then 1 is just 1, so it'll become x squared plus 1. But since there's a negative on the outside, we have to flip the signs. Then x minus 3 squared is going to be x squared minus 6x plus 9. And that will pretty much be the final step before just tidying it all up. Is equal to this. Then, after simplifying, 2x squared minus x squared will be x squared. Then, negative 6 minus 1 is minus 7. Then, all of this will be divided by x squared minus 6x plus x squared minus 6x plus 9. And that will be our final answer. Now, what you can also do is you don't exactly have to expand x minus 3 squared if you don't want to. I just chose to because why not? And also, some people might have you, some like textbooks and stuff might have you expand everything, or some people would rather have you keep it factored. And here's the solution. Over here, I decided to put it where it's still factored and not completely expanded. And we have u and v identifying the functions, finding the derivatives, applying the quotient rule, and substituting and simplifying. Our next example is to find the derivative of g of x is equal to sine of x over cosine of x. And in fact, we can actually do this two ways. Number one is understanding that sine of x divided by cosine of x is in fact tangent of x, so g dash of x is equal to d by dx of tangent of x, and that's equal to secant squared of x, which is a pretty simple answer. But also this says to find the quotient rule, so it'll almost be like a proof that the derivative of tangent of x is equal to secant squared x. So let's apply the quotient rule. I won't state the entire formula, but just go straight into substituting. So if we say u dash is sine of x and u is sine of x and v is cosine of x, that means we have u dash v, so cosine x times cosine of x. After that, we'll have negative. Now, if we have the rest, it'll be sine of x times the derivative of cosine of x, which is negative sine of x. Now, all of this is divided by cosine squared x. So, that's going to be the first step in the next method. Now, after that, what we need to do is we need to start simplifying and substituting everything. So, cosine of x times cosine of x is cosine squared x. Then, negative sine of x times sine of x is negative sine squared of x, but since there's a negative on the outside, everything cancels out, and this just becomes sine squared of x, and divide by cosine of x pretty much just stays divided by cosine of squared x. Now, what you might notice is that cosine squared x plus sine squared x is a Pythagorean identity, and it's proven to equal 1. So, we'll have 1 divided by cosine squared of x. And since 1 divided by cosine of x is secant of x, that means 1 divided by cosine squared of x is equal to secant squared. And there you have it, the proof using the quotient rule that the derivative of tangent of x is equal to sine of secant squared of x. Now, if you remember my last video proving all the derivatives, if in fact you knew how to prove the quotient rule beforehand, because none of them are actually related, you don't need one to prove the other. Therefore, you can use a different method, just proving sine of x and cosine of x, and then substituting different values for everything, and figuring out the derivatives of each of the other 4 trigonometric functions. So that's about it, really. Now I decided to throw this example in there to show how the quotient rule also connects or ties up with other aspects which you thought might not be exactly related. And proving them doesn't have to be related, but it can be, and you saw that actually saved a decent amount of time than just plugging and chugging through the limit definition and doing a lot of algebra. A quick review of when to use each rule. Number 1, product rule is when we have 2 or more functions multiplied together, and the quotient rule is when you have one function divided by another. But an alternative to the quotient rule is rewrite as product and use the product rule plus the chain rule. Now, we have not covered the chain rule, but I'll also cover that slightly in the chain rule video, where I discuss how one can use the quotient as a product rule plus the chain rule. And over here it states how to exactly do that, saying g of x times to the power of negative 1. Then what we do is we do the derivative of we do the power rule, then we do the derivative of the inside function, but that's not important since in this video we're not talking about the chain rule. And a few common mistakes before we go into a more complicated example where it requires both rules. Writing that the derivative of a product of functions is not the product of their derivatives. This is wrong. That's why the special rules for the product and quotient rule are there. Then the quotient rule order is mixing up the subtraction order, because in the product rule, since it's plus, you can do either way, but since it's subtraction, there is one specific order. Then forgetting to not squaring the denominator in the quotient rule is another big mistake. The fourth is sign errors, especially with negative functions or functions that have a negative derivative. And simplification, not simplifying the final answer, because many times exams will take off points if you don't have it fully simplified. Here is a more complicated example to pretty much finish off the video, as I wanted to show you how both of these rules, plus the power rule, plus the derivative of the trigonometric functions, can all be used in hand. Alright, so let's get started. I won't state much of the rules, as that will take a very long time stating each of the rules. But first, recognize that x squared plus 1 times sine of x is a product. So let's say x squared plus 1 times sine of x is one function f of x. So f of x is going to be equal to x squared plus 1 multiplied by sine x. Now, how we're going to differentiate this is using the product rule. So, in the new line over here, what we're going to write is f of x is equal to, using the product rule, if x squared plus 1 is equal to y of x and sine of x is equal to z of x, that means the derivative of x squared the derivative of x squared plus 1 is 2x times sine of x, then plus the derivative of sine of x times x squared plus 1 multiplied by the derivative of sine of x, which is cosine x. Now, what we can do is we can simplify this. So, 2x of x plus what we have is x squared plus 1 times cosine of x. So, x squared cosine plus cosine x. So, that is pretty much the full simplified form of f dash of x. Now, that's just one piece of the puzzle, because we're not done yet, because that was only the derivative of the top half. Now, what we need to figure out is the derivative of everything. So, h of x, if we already identified the top half as f of x, that means we can say that pretty much everything, like the top line, is f of x. So, h dash of x, using the quotient rule, will be equal to f dash of x times g of x, which we can say is the denominator, times g of x minus f of x times g dash of x. So, it's pretty much the entire function. Then we divide that by g squared. So then, since we already figured out f dash of x, we can start substituting. So if x is equal to f dash of x, which is equal to 2x sine x plus x squared cosine x plus cosine x multiplied by g of x, which is x minus 2, minus f of x, which is squared plus 1, multiplied by sine of x minus times g dash of x, which is just equal to 1. Now, all of this is divided by g dash of x squared, which is x minus 2. So we square x minus 2 in the denominator. That is pretty much the first part of solving the full problem after we figured out what f dash of x is. Then, after that, we have to do some more simplification, which first involves expanding everything. So what happens is we have h dash of x is equal to 2x sine x, then all of this times x minus 2. So if we multiply everything by x, so that will be x. Then for minus 2, basically minus 4 times x sine x minus 2x squared cosine x, then minus 2 times cosine of x, so just minus 2 cosine of x. And keep in mind that's pretty much only the first part of the entire equation. And the next part is just x squared plus 1 times sine of x. So it'll be x squared sine of x plus sine of x. And since there's a subtraction sign, we have to flip all of the signs. Now, I'm going to keep x minus 2 squared the way it is, or you could also expand that. And that's the next step in solving this equation. Now, after this, we need to do yet more simplification than we've already done. So, the next thing that we need to do is continue the simplification, which involves using like terms. So, we have 2x squared sine x, and we have negative x squared sine x, so that just becomes x squared sine x. Then, what we have is 2x squared cosine x, but there's nothing over there, so that stays. 4x sine x, there's nothing over there. So according right now, pretty much everything is staying constant, but we can also factor a few things out, like cosine of x and sine of x. What we can do is we can group all the sine of x and the cosine of x terms together. So minus 4x sine x, that means this won't be here. Then with the next sine x is minus. Then after that, we remove this and we have a few of these terms all grouped together. 2x squared cosine x, just to make sure everything is in order. X cosine of x, and this is pretty much over here. Then what can happen is this, after we can also factor a few things out. So in the first three terms we can factor out sine of x times x squared minus 4x minus 1. Then after that, what we can do is we can say minus cosine x multiplied by cubed minus 2x squared minus 2x squared minus 2x squared plus x minus 2. Now all of this can be divided by x minus 2 whole squared. So now with this example, you pretty much realize how complicated it can actually get to solve some of these problems. So solution is over here, where they didn't even remove everything. They still decided to keep a lot of stuff after factoring out and simplifying a few more times, because the term over here, x cubed minus 2x squared plus x minus 2, which we had over there, can also be simplified into x squared plus 1 times x minus 2. Now a few more things before we go. The extended product rule for 3 or more functions, just what you have to do is you have to take turns pretty much putting one derivative in the first term times the other two normal functions, then the second derivative in the second term, and the third derivative in the third term, and so on. Basically taking the derivative of each function one at a time, keeping the others just as their function. And over here, here's an example where we have 3 functions and we calculate the derivative. Here is basically finding d over, these are a few practice problems. The first one is to find d over dx of x cubed plus 2x times e to the power of x. And if we haven't covered it already, the derivative of e to the power of x is equal to e to the power of x, and the derivative of the natural logarithm of x is equal to 1 divided by x, because it's a little confusing how all of that works, but I'll definitely do a video in the future showing that. Then finding, instead of tangent of x, since we already covered that, find d by dx of cotangent of x using the quotient rule. Here are the few rules over here, the product rule and the quotient rule. Always remember the order and the signs in the quotient rule. Always simplify your final answer. And these are some of the fundamental rules for differentiating complex functions, and practice is always key to mastering each of these techniques. And thank you so much for watching this video. It really means a lot to me, and I hope you come back in the future. If you like these videos, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And please make sure to comment down below any suggestions, tips, or questions for the channel you have. I'll be free to answer pretty much all questions you have. So thank you so much. Thanks for watching. See you in the next one, and bye-bye.